Hi everyone, my name is Filippos Kozakos, and here is my Lab 5 presentation about a falling slinky. So for our introduction, the goal of this experiment was to determine the effects of gravity and drag force on the motion of a slinky object who falls downwards. In this experiment, I have also generated two position versus time graphs. The first graph is from the tracker, and the other graph is from the computational model. Some fundamental physical principles. First, the Newton's second law, which is the update of the position formula using the velocity, average velocity. Then the velocity update formula, as you can see with F net, the weight force, which is minus mg, then drag force, which is minus bv squared, where b is the drag coefficient. Here is my tracker video that I analyzed, and here are in the right are the results. So let's take a look at it. As you can see here in this point, the bottom of the slinky stays stationary. We're gonna get into that later. I'm gonna explain why that happens. And then you can see right after this point, then it starts to drop down. So the data measurements from the tracker model, we knew that the mass of slinky was about 0.204. The initial position was the following. The final position was the following, captured from the tracker, and the calibration stick that I used in my tracker model was about 1.75 meters. Here is my gloss script code, initial conditions. I used the ball mass, the initial position of which is a vector, the ball velocity. I have used the drag coefficient, which I calculated through trial and error. Here, at part one of the code simulation, this is my first while loop. I found the force of tension. I found the weight force, and then the F net is just the sum of them. Also, the update the object's velocity formula and the object's position update formula. Part two of my code simulation, I use another while loop. I said while t is less than 1.630, which is the time of last observation on tracker. I calculate the net force, which in this case, the drag force is included, the weight force, and I just add them together to find the net force. And then I update my velocity and also updated my position formulas. This is my model versus observed graph comparison. As you can see, the model position line up well with the observed position, except somewhere in the middle. The straight blue line is due to the stationary bottom part of the slinky, and then deviation can be explained due to error in the tracking points on tracker or an error in the length of the calibration stick that I used. So why does the bottom of the slinky remain stationary? This is the question of this experiment. The tension force of the slinky is equal to the force of gravity. So therefore, they cancel out. So the bottom of the slinky is in static equilibrium because the two forces acting on it, as I mentioned previously, the tension force and gravity, are opposite and equal. So let's go through the what if question. What if we add a tennis ball at the bottom of the slinky and then let the slinky fall? Here is the video representing that what if question. Here is the tennis ball with some mass and then it's stationary. And then it just drops. This follows the exact same principles from our previous example, this one, without the mass. So observation of what if, The previous video has shown that the foiling motion will be the exact same, and the principles that we are discussing in the slab experiment will be sufficient when we add the tennis ball at the bottom of the slinky. I hope that this makes sense, and thanks for your time and for your attention.